All right, everybody, it's time to start Unit 2. Unit 2 covers Chapter 3, which is all about differentiation rules. We are used to finding derivatives already. We've been finding them using these long limits, right? Well, those days are over. Starting off in section 3.1, we're going to look at derivatives of polynomial and exponential functions. Remember that in the previous chapter, we used the limit definition to find derivatives, which, as we know, took quite some time. But in this section, and in the next couple of sections, we're going to look at differentiation formulas that allow us to find derivatives without having to take the limit. Yay! Think of all this time you're going to save. So let's look at some of these rules. Our first rule is about the constant function. If you've got y equals c as a constant function, then the derivative of that constant is 0. That makes sense, right? Think about the derivative as the slope of the tangent. How steep is a constant function? Yeah, a constant function looks like that. It has 0 steepness. So the derivative of a constant is 0. Next, let's look at the power rule. This is the general version. If n is a positive integer, then if we take the derivative of x to the n, the derivative is going to be n times x to the n minus 1. This is a nice rule. This is a nice rule. So kind of think about this. If I have x to the n and I need to take the derivative of that, what I'm going to do first is I'm going to take this n value, this power here, and that's going to come down the front. And then the x stays as is. And then coming back to my exponent, I'm going to reduce that by 1. This is always going to be true. If I have a constant times some function, then that constant just goes along for the ride. That constant just goes in the front of the derivative of that function. If I'm adding functions together and I want to take their derivative, then I just individually take the derivative of each function and then add those together. Same thing with the difference rule. And here's a neat one that often stumps people, is that if I'm taking the derivative of the exponential function e to the x, it gives me just e to the x. Now this is the set of derivative rules without the chain function, so it's really important that all of these things just involve an x, okay? All right, you'll see what I mean in a second. Let's do some examples. All right, so I've got y is equal to 7. So if I'm taking the derivative with respect to x of y, then I'm taking the derivative with respect to x of 7. All right, what's the derivative of a constant? Yeah, it's 0. Well, that's it. Okay, so f of x is equal to x to the 24. Then f prime of x is going to be equal to, take this power, bring it down to the front. So this is going to be 24. And then we leave the x alone. And then I'm going to take this power and I'm going to reduce it by 1. So the derivative becomes 24 times x to the 23rd. For the next one, I got a little hint for you. For this function right here, keep in mind that if you have the cube root of t squared, That's like saying t to the 2/3 power. And it is much easier to take the derivative when we use t to the 2/3 power. So that's what we're going to do. So I'm taking the derivative with respect to t of t to the 2/3. Remember what I'm going to do. I'm going to take that power and I'm going to put it down in the front. So this power, I'm going to put down in the front. So it's going to become 2/3. The t goes along for the ride. And then for my exponent, I need to take 2/3 minus 1. I'm going to write it out for this one because I want to show you a trick. Whenever I'm subtracting 1 and I've got fractions going on, I just use my denominator. Since this is 2/3, I'm going to subtract 3/3 from it. What I end up getting is 2/3 times t to the negative 1/3. Now, since this function started off as a root, I need to keep it in root form. So t to the negative 1/3 is like saying two things. First of all, it's saying that t to the 1/3 is in the denominator. And then that 1/3 is like saying the cube root. So that's going to be my final answer. So I'm going to have 2/3 times the cube root of t. And then that ends up being my final answer. For the next problem, this also goes smoother if we rewrite it. So instead of using 1/x², let's use the rule of exponents and turn that into x to the negative 2. Then we can take the derivative of that. We're taking the derivative with respect to x. So once again, I'm going to take that power, negative 2, and I'm going to bring it down into the front. So I'm going to have negative 2. I'm going to leave the x alone. The x goes along for the ride. And then again, I'm going to show this step. I'm going to take the power of negative 2, and I'm going to subtract 1 from it. And I'm going to get negative 2 times x to the negative 3rd. Well, notice my original problem is in fraction notation, so I want to make sure that my final answer is also in fraction notation. Oops, I'm getting a little too low to notate there. I forgot I can erase. So instead of writing negative 2 times x to the negative 3, I'm going to write it with the x in the denominator. So this is going to be negative 2 over x cubed. And that's going to give me my derivative. Okay, so now we have this function. F of t equals 2 divided by t cubed. So again, how can we rewrite that? If I have 2 over t cubed, how can I rewrite that as 2 times t to some power? Yeah, because we want to simplify it, so make it easier to use the derivative rules. So I'm going to write it as 2 times t to the negative 3. Then I'm going to take the derivative of that. So I'm going to take the derivative with respect to t of 2 times t to the negative 3. Okay, so I'm going to take this power, and it's going to come down. And even though there's a 2 down there, I'm going to multiply them together. So I'm going to have negative 6. And then I keep the t. And instead of writing it as to the negative third, I'm going to take it as the negative 3 minus 1, because I always subtract 1 from the power. And then I'm going to get negative 6 times t to the negative 4. And then my last step is to write it as a fraction again. We're just using a lot of the power rule here, folks. That's really all that it is. This is one of those problems that I'd like to try on your own for a second. Go ahead and pause the video. Find g prime of x and see if you and I can match. All right, welcome back. I'm trying to take the derivative with respect to x of g of x. That will give me g prime of x. And I'm going to take the derivative of each thing. All right, so this 4 is going to come down. So I'm going to have negative 4 over that 2 times x to the 4 minus 1, so that's going to give me 3. Now I'm going to take the derivative of the next term. So I have 3x to the third. I'm going to take the 3 and bring that down to the front. So 3 times 3 is going to give me 9. And then I keep the x, and then I reduce the power by 1. So I'm going to end up with 9x squared. For the next term, I've got a negative 2x. Now this is just a plain Jane x. So what's the power on x? Yeah, it's just 1. So I'm going to bring that power down. Negative 2 times 1 is going to give me a negative 2. Keep the x. And then I'm going to reduce the power by 1. So I'm going to have 1 minus 1, which is going to give me 0. Right? Good. And then my last term is a constant. So what's the derivative of a constant? Yeah. It's 0. Perfect. All right, so we're just going to clean that up and put that as the answer. So for my first term here, I can simplify the negative 4 and the 2. So that's going to simplify into negative 2 x cubed. For my next term, my plus 9x squared can't be simplified any more than that. So that's going to go along for the ride. For the third term, I'm going to simplify that. That negative 2 times x to the 0 is just like saying negative 2. And then for the plus 0, I don't have to write that. Everything is plus 0. We don't include that, do we? Nope. Well, so my derivative of this function is going to be negative 2x cubed plus 9x squared minus 2. Okay, so let's use this like we would have done for a problem in a previous section. So here I've got this curve, f of x, which is x to the 4 minus 5x squared plus 4. And they want me to find the equations of the tangent line and the normal line, which is perpendicular to the curve at point 1, 0. Graph the curve and the lines on the same window. Well, I'm going to do the graphing first because I want you to see what it looks like. So we already know that the point 1, 0, that's right here. And if I were to draw the tangent line, that's this orange guy. And the normal line, this is a new concept, but the normal line is always the perpendicular line to the tangent. So remember how perpendicular relationships are. So if I have the slope of the tangent, and I know what that is, I can find the slope of the normal by taking what? Do you remember? What's the relationship between perpendicular lines? Yeah, they are the negative reciprocals. So I want to find the slope of the normal after I find the slope of the tangent by taking the negative reciprocal. And then they want us to graph it. So I did the graphing first. I cheated a little bit, but you guys can graph that on your own once we find the equations of the line. Okay, let's do it. All right, so remember, if you're trying to find the equation of your tangent line, you need to first find the slope of your tangent at that x value. Next, you need to find the equation, and that's where we use that point slope formula. Okay, and then we're actually going to do this twice because we're also doing it for the tangent and the normal. All right, so let's do the tangent first. So first thing I'm going to do is I'm going to find the slope of the tangent, and this is the slope of the tangent at any x value. And I'm going to find that just by taking the derivative. So look at this first point here. I've got x to the 4. I'm going to take that power and bring it down. So I'm going to get 4x. And then I'm going to reduce that power by 1. So I'm going to get 4x cubed. Now for the next term, I've got negative 5x squared. So I'm going to take that power and I'm going to multiply it by the negative 5. And then I've got the x goes along for the ride. And then 2 minus 1, well, that's just going to just give me a 1. So there's the derivative of that second term. And then the derivative of a constant is just 0. So the slope of the tangent at any point x is going to be 4x cubed minus 10x. All right, perfect. Now, I want to keep in mind, I'm not doing this at any point. I am doing this specifically at the point 1, 0. So now I'm going to find the slope of the tangent at x equals 1. So in other words, that's going to be f prime of 1. So I'm going to take my tangent function, my derivative function, and I'm going to plug in x equals 1. And I get 4 times 1 cubed minus 10, and that's going to give me negative 6. So the slope of the tangent at this particular point at x equals 1 is equal to negative 6. All right, so that's my first part. I found my slope of the tangent. Second part is the equation. So that's where I do my y minus y1 equals my slope times x minus x1. So my y coordinate for this point is 0. So I'm going to plug 0 into my y1. My slope of the tangent line at this point is negative 6. So for my slope, I'm going to plug in negative 6. And then my x coordinate is 1. And then this is a quick one to solve. I just have to distribute out the negative 6. And I'm already solved for y. So the equation of my tangent line is going to be y equals negative 6x plus 6. And if you graph that on your calculator, you'll see it looks like this orange line that I've got here that I'm just now coloring over with blue, and I'm going to erase it so you can see it again. All right, next we're going to find the normal line. So first thing I need to do is I need to find the slope of the normal, but I know it's the negative reciprocal of the slope of the tangent. So I don't even have to find the derivative or plug stuff in. I'm just going to take the slope of the tangent, which as we know is -6, and I'm going to do the reciprocal of that, and it's a negative over and this will simplify into 1/6. Next, I'm going to do that equation. So I'm going to have y minus y1 equals m times x minus x1. And I'm going to plug in my y coordinate and my slope of the normal and my x coordinate. And then this one I can solve pretty easily just by distributing the 1/6 out. And if I graph that normal line, I'll see that it looks like the yellow line, and that it's perpendicular to my tangent. Next type of problem. They want us to find the points on this curve, x cubed plus 3x squared plus x plus 3, where the tangent is horizontal. Right? So sketch the curve and the horizontal tangents. So first of all, I want to highlight where you're going to see horizontal tangents. Horizontal tangents happen at maximum values and minimum values, or values where the graph just kind of levels off. Like let's say you have a graph that kind of looks like that. That would be a horizontal tangent as well. Horizontal tangents, as you know, have a slope of what? All horizontal lines have a slope of what? Yeah, slope of 0. So what we are going to do is we are going to take the derivative. We're going to find y prime, and we're going to set that bad boy equal to 0. And that's going to give us the x values of where the minimums are. I don't know if it goes right on 2. I'm just tracing that over. All right, let's do it. This is a bit of work. Okay, so first thing we need to do, because we're looking for horizontal tangents, or specifically where the tangent is horizontal. So the first thing we're going to do is we're going to find the slope of the tangent at any x. We're going to find the slope of the tangent at any x. So that means we're just going to take the general derivative. So for this first term, we're going to take the 3 and bring it down in the front. And then I reduce the power by 1, and that becomes 3x squared. For my second term, I'm going to have the power of 2. That's going to come down in the front. And then I'm going to reduce it by 1. And the derivative of that turns into 6x. For my third term, I take the power of 1, I bring it down. And then I reduce my power of x by 1. That gives me x to the 0. Which is really just like saying what? Yeah, 1. And then remember that the derivative of a constant is 0. So when I take the derivative of 3, I'm just going to get plus 0, which I don't need to write that down. All right, so I found the slope of the tangent at any value y. Now I need to remember for horizontal tangents, that's when the slope of the tangent is equal to 0. So that means that y prime is going to equal 0. And in this case, since I just found y prime, I'm going to set that equal to 0. So I'm going to say, okay, 3x squared plus 6x plus 1 equals 0. Now, what I'm going to do at this point is say, all right, I've got to solve this for 0. I would factor this, because this is quadratic. Notice that this is a quadratic function. And so the way that we deal with quadratic functions is you always just set them equal to 0 and you solve, you know, with factoring or the quadratic formula. It's up to you. Okay. But this one doesn't factor. I can see that right now. So I know already I need to use the quadratic formula. So that's what I'm going to do. So I'm just going to highlight my A, B, and C values. And I'm going to use the quadratic formula to find out for what x values is this thing going to give me 0. So remember your good old buddy, the quadratic formula. We've got negative b plus or minus the square root of b squared minus 4ac all over 2a. So here's my a, here's my b, here's my c. And again, this thing has to be equal to 0 in order for all this stuff to be true. And it is. It's equaling 0. So I'm going to start plugging it in. All right, negative b is going to give me a negative 6. So I'm going to have negative 6 plus or minus. Going to have 6 squared minus 4 times my a value. Remember that a is 3. Times my c value. Remember that c is 1. And I need to take the square root of that. And that's going to be all over 2 times a, which is going to be 2 times 3. Okay, so I'm going to end up with, bring it up here, x equals negative 6 plus or minus. We're going to do the square root of 36 minus 4 times 3 times 1, which is going to give me the square root of 24. And that's all over 2 times 3, which is 6. I need to break that up. So the square root of 24 is like saying 6 times 4. And I can take the square root of 4 and pull that right out, right? Okay, this pesky little guy right here, this little 4, he can come out of the square root because you can take the perfect square root of 4. And that'll give me a 2. So I'm going to have negative 6 plus or minus 2 square roots of 6 all over 6. Well, now I need to split that up and do some simplifying. So I'm going to take this denominator of 6, and I'm going to split it amongst the 2 terms on the top. So I'm going to have negative 6 divided by 6 plus or minus 2 square roots of 6 divided by 6. And then I'm going to simplify that. So I'm going to have x equals negative 1. And I can reduce this piece here. And then this piece here, be really careful when you're reducing it. I've seen a lot of students do it in a very interesting but very incorrect way, is that you can't cancel the 6's. Yeah, no. That 6 on the top is inside a square root. That's like a little protective covering, okay? So you can't cancel that 6. You can, however, let the 2 and the 6 cancel each other. So 2 6's is like 1/3. So this turns into the square root of 6 over 3. All right. So this means then that the x coordinates, the x values, okay, the points where this equation has horizontal tangents is going to be when x equals -1 minus square root of 6 over 3 and -1 plus the square root of 6 over 3. Now, in this case, I actually just want you to find the x coordinates. If you needed to find the y coordinates as well, you'd have to take those x values that we just found and plugged it back into the original function y. So just keep that in mind. Sometimes we need to find more than one derivative. So when that's the case, the first thing I would do is I would rewrite your original function so that it's easier to differentiate. So like for this one, the only thing I'm going to rewrite is that 5 over t. I'm going to write that as 5 times t to the -1. So I'm going to take y prime, which is I'm going to take the derivative with respect to t. So for my first term, I'm going to take that power 3 and bring it down in the front. So this is going to become 3, then reduce the power by 1, and I get 3t squared. For my next one here, I'm going to take this -1 times this negative, and I'm going to end up with a positive 5. Okay, so -1 times -5 will give me a positive 5. And then I need to reduce the power, so I'm going to have t to the -2. For the next one, be careful. The +2 is going to go along for the ride, but do you remember? What's the derivative of e to the t? Yeah, for right now, it's just going to be e to the t. So that's it. Whenever we take the derivative of the exponential function, it's just itself. Don't worry, it'll change later. Like if we had to do e to the t squared and take the derivative of that, that would be different. But that's in your future. No fears. We'll learn how. Okay, if I need to find y double prime, that means I need to take the derivative again. But I need to take the derivative of y prime. So I need to take the derivative of the first derivative. So that's what I'm going to do. For this first term here, I'm going to take the 2, and it's going to come down in the front. So 3 times 2 is going to give me 6. And then I'm going to reduce the power. So I'm going to get 6 times t to the 1. Over here for my second term, I'm going to take this -2, and it's going to multiply by my positive 5, and I'm going to get -10. And then my power is going to be reduced by 1, and so this is going to become -10 times t to the -3. And for my last one, that +2 goes along for the ride. And then do you remember what's the derivative of e to the t? Yeah, it's e to the t. It is its own derivative. Perfect. All right. That is my second derivative. I have a few extra examples that I want you guys to do, specifically because there's a lot of hints that are involved with these problems. First of all, let's take a look at these two problems. So these right here, notice that you've got a binomial times another binomial. And in the next section, we're going to learn this thing called a product rule. But in the meantime, if we don't have the product rule, we've got to do it without the product rule. So what you need to do is multiply it first. So FOIL it out, or distribute, or however you think about it. All right, so when I FOIL this out, I'm going to get 3u squared. And then I've got negative u and plus 6u, so it's going to be plus 5u. And then negative 1 times positive 2 is going to give me negative 2. Now I can find the first derivative more easily. I have to FOIL first, okay? Even when we get into the next section and you have the product rule, it's a lot easier to FOIL this than to use the product rule. So keep that in mind. All right, so if I'm taking the derivative, I've got this first term here. I'm going to take the derivative of, I bring the power of 2 down, so I'm going to get 6 times u to the 1, because I reduce the power by 1. Then I've got my next term of 5u, so I'm going to have 1 times 5, and then I'm going to have u to the 0, which means that the u goes away. And I take the derivative of negative 2, which is just 0, and so I don't have to write it. And so I get the derivative of h, which is 6u plus 5. All right, let's look at this next problem. Same thing. I want you to multiply this out. Okay? So before we take the derivative of r, what we need to do is we need to multiply this binomial out first. Now don't forget, when you square a binomial, you get out a trinomial. Most students forget that part. They forget the 6a, the middle term, but it's true. That's what you get. All right, now that I have it written in that form, now I can easier take the derivative. So looking at my first term here, I'm going to take the 2 times 9. That's going to give me 18. And then I'm going to reduce the power by 1. So I'm going to end up with 18 times a. For my next one, I'm going to take the power of 1. I'm going to multiply that by the 6. So I get plus 6. And then it becomes a to the 0. And so it just ends up being plus 6. And then the derivative of 1 is 0. So I don't have to write that down. So I end up with 18a plus 6 for my derivative of r. These two problems here have similar tricks you need to do. For this x to the cube root of x, write it as x to the 1/3 power. And then distribute that out. Okay. So y is like saying 2x to the 1/3 plus x to the 4/3. Because remember, when I multiply this out, this is x to the 1. 1 plus 1/3 is 4/3. Now, even though we know that 4/3 is the same as saying 1 and 1/3, you don't ever write a power as a mixed number. You always write a power as an improper fraction. Always, always, forever, not men. Yeah. Once I have it written in this form, I can go ahead and take the derivative. So remember what I do. I'm going to take this power. I'm going to multiply it by the number in front. So I end up with 2/3. Whenever I multiply a fraction by a whole number, I just multiply the top by the numerator, or the whole number by the top, or the whole number by the numerator. And then for x to the 1/3, remember I'm going to reduce that power by 1, so I'm going to subtract 1 from 1/3. So 1/3, if I subtract 1, is like subtracting 3/3. Okay, I'm going to write right below it so I've got a spot to simplify. So I'm going to have x to the negative 2/3. All right, now time for the second term here. So I've got x to the 4/3. The 4/3 power is going to come down in the front. So I'm going to end up with plus 4/3. Actually, let me write it here. Plus 4/3. Then I'm going to have x to the 4/3 minus 1. And that's going to give me x to the 1/3. However, note that this function here is written in root form. So typically when you have a function written in root form when you start, they want you to write it in root form when you finish it. Okay, I know it's kind of weird, but they do. So if you want yours to match their answer, you're going to want to do that. So first thing I'm going to do is I'm going to rewrite this in root form. And because that's a negative 2/3, that thing ended up in the denominator. And then the second one here is a positive 1/3, so that just ends up like that. Okay, now I want to combine like terms for this, but I can't do it because I don't have an LCD. So I need an LCD. All right. So the LCD here, whether you believe me or not, the LCD is going to be 3 times the cube root of x squared. So this second one here has the 3, but it doesn't have the cube root of x squared. So I'm going to do the cube root of x squared and multiply top and bottom of that second fraction by that value. And I'm going to bring my work up here. So my y prime is going to be equal to, here I've got 2 for my numerator, plus, here for my next one I've got 4. Here I've got x to the 1/3, so the cube root of x, times x to the 2/3, or the cube root of x squared. And if I multiply those x's together, I just need to add their powers together, and that's going to give me x to the 1. I know, right? Crazy. Don't know why that just happened. That's going to give me x to the 1. Cool, huh? And then in my denominator, I just got this 3 times the cube root of x squared. Sweet, huh? Okay. All that last stuff, that's just simplifying. And when it comes down to it, it's not really worth that many points. If you got it to this step here without the yellow, I'd accept it. However, if I had to find the horizontal tangents of this derivative, I would need to be able to write it as this fraction because I have to set the numerator equal to 0 and the denominator equal to 0 in order to find possible horizontal tangents. Also some other stuff that we do, but yeah. Anyways, okay. So make sure you know how to do that for your future self. Okay, for the next one, I'm just going to rewrite that cube root of x in the denominator as an x to the negative 1/3, and then I'm going to take the derivative. When I take the derivative of the first thing, e to the x goes along for the ride, and the 3 goes along for the ride. The derivative of e to the x is e to the x, so I'm just going to leave it. All right, next, I take my power of negative 1/3 and multiply that by the 4, so I'm going to have negative 4/3. And then I'm going to reduce that power by 1. So I'm going to end up with negative 4/3 times x to the negative 4/3. Now this one right here, just to simplify that, I've got 3 e to the x minus 4 divided by 3 times the cube root of x to the 4th power. Now I would have you leave it like that, but notice something. Do you see how the power inside the cube root is bigger than the index of the cube root? In other words, what we've got there is a 4 inside a cube root, and that's a big time no-no. So what I'm going to do is space it out. So if I take the cube root of x to the 4, that's going to be an x that gets to come out and an x that's left behind. Okay, so really what I just did was I took the cube root of x to the 4. And what that is an x gets to come out and an x is stuck behind. All right, and then that is my derivative. Again, if I have to find the horizontal asymptotes or if I need to do some other work with it, which we'll do in later sections, I do need to write this as one fraction, but you don't have to for now, so we can just leave it like this. All right, I got a couple more examples here for you. If we need to differentiate this function, notice that it's a rational function and we don't have a quotient rule. We're going to learn a quotient rule, but we don't have one yet. So right now I need to use the distributive property and distribute the square root of x through all of these. So I'm going to have x squared divided by the square root of x. And then the next term, 4x, I'm going to divide that by the square root of x. And then I'm going to have 3, and I'm going to divide that by the square root of x. I still can't leave it like that. If I leave it like that, it's too difficult to differentiate. We haven't used a quotient rule yet. And even if we did know a quotient rule, using the quotient rule for this would be like overkill. We just want to use rules of exponents. So basically, I'm going to take the power of the top, x, and subtract from that the power of the bottom, x. So this would be like 2 minus 1/2. For the next one, I'm going to have plus 4. That's going to go along for the ride. And I'm going to do the power of the top x, which is 1. And I'm going to subtract from that the power of the bottom x, which is 1/2. And for this one, I'm going to have plus 3, and then since there's no x in the top, I'm just going to write that as x to the minus 1/2. All right, so then I'm just going to rewrite these in final form. 2 minus 1/2 is going to give me 1.5, which is really 3/2. For the next one, 1 minus 1/2, that's just going to give me 1/2. And for the last one, I've already got that written down to the negative 1/2 power. Now I need to take the derivative with respect to x of that function. That will give me y prime. So now I'm going to take the derivative of that y, and that's going to be my y prime. So for my first term, I'm going to take that 3/2, and that's going to come down in the front, 3/2. And then I'm going to reduce that power by 1. Reducing it by 1 is 2/2. Then I'm going to do the next term. I'm going to take the 1/2 and multiply that by the 4. So that gives me 4/2. And then for my x, I'm going to reduce that power by 1. So I'm going to reduce it by 2/2. And for the next one, I'm going to do the same thing. And I'm going to reduce the power by 1, which is 2/2. And then I'm going to simplify stuff. So I've got 3/2. For the front, that is left, that's going to give me 1/2. Next one, I've got 4 divided by 2. That gives me 2. And then 1/2 minus 2/2 is going to give me x to the negative 1/2. And then minus 3/2 is going to go here. And then I'm going to have x, the negative 1/2 minus 2/2. And this is going to give me x to the negative 3/2. And then remember that your original function was written in root notation. So you're going to want to rewrite these for root notation. So I'm going to write this as 3 square root of x over 2 plus 2 over the square root of x minus 3 over 2 square root of x cubed. But then that last one can be simplified because we got a x cubed inside a x squared. So I'm going to rewrite my final form up here. So my y prime is going to be 3 square root of x over 2 plus 2 over square root of x minus 3 over 2 x square roots of x. And then you can write your final answer like that. But again, if you need to do some work with that, you'd have to use an LCD. Specifically, the LCD in this case would be 2x square root of x. And then you'd need to turn that into one fraction. So if you had to do that, keep that in mind. All right, for this function here, we're just going to find f prime, f double prime, and f triple prime. And since we're finding so many derivatives, we're not going to really do any simplification between each one. We're just going to find them. All right, okay, so for f prime of x, I'm going to take this 4, I'm going to bring it down. So 4x, I'm going to reduce the power by 1, so I'm going to get 4x cubed. For the next one, I'm going to have the 3 come down, so I'm going to have negative 9x, and then I'm going to reduce the power by 1, so I'm going to have negative 9x squared. For this one, I'm going to have the 2 come down, and I'm going to have negative 12x, and then 2 reduced by 1 is 1, so I'm going to have x to the 1. And then here, I'm going to have the exponent of 1 times 7 will give me 7. And remember that this gives me x to the 0, but x to the 0 is 1, so I don't have to rewrite that here. Next, I've got this derivative. The negative 3 goes along for the ride, and the e to the x goes along for the ride. Oh, and then this one, I actually forgot to rewrite this one. This is going to be 4x to the negative 1/3. So when I take the derivative of this, I'm going to take the 1/3, bring it down in the front. So I'm going to have negative 4/3 x. And then I'm going to subtract 3/3 from that, and that's going to give me negative 4/3. Okay, remember what I said? You don't have to simplify this any more than that. But that's going to be my first derivative. Okay, second derivative. Let's do this. All right, I'm going to take the 3 times 4. That's going to give me 12. Reduce the power by 1. That's going to give me 2. Then I'm going to take the 2 times the negative 9. So that's going to give me negative 18. And then I'm going to reduce this x squared to an x to the 1. This 12 is like saying this negative 12x is like saying x to the 1. So I'm going to take 1 times negative 12, which gives me negative 12. The x turns into x to the 0, so I don't have to write that down. The derivative of 7 is 0, so I'm not going to write that down. And then I've got this negative 3 e to the x, which when I take the derivative of that, the negative 3 goes along for the ride. The e to the x goes along for the ride. And then when I take the derivative here, I've got that negative 4/3 times negative 4/3. That's going to give me positive 16/9. And then I'm going to subtract another 3/3 from the negative 4/3 because I'm going to subtract 1 from 4/3, and that's going to give me negative 7/3. And then that's going to give me my second derivative. For my third derivative, I'm going to take the derivative of my second derivative. So I'm going to have 2 times 12, which gives me 24. And then I'm going to reduce the 2 by 1, so I get x to the 1. This is a negative 18x, and so I'm going to take the power of 1 by negative 18. That gives me negative 18. The x goes poof, disappear, bye-bye. It turns into x to the 0. Take the derivative of the negative 12. That also goes poof, disappear, because that is 0. I take the derivative of negative 3 to the x. Notice that nothing happens to it again. It just has no effect on it. And then here, when I take this derivative, I'm going to have to do negative 7 times 16. So I'm going to get negative 112. And then 9 times 3, which will give me 27, all over x. And I'm going to reduce this by 1. So negative 7/3 minus 1 is going to be negative 10/3. And then that's my third derivative. So third, second, and first derivative. Fun, huh?